Hi everyone, this is Mr. Lee. In this video, we are going to go over spring potential energy. All right, let's begin. So if you remember from the previous video, we defined potential energy as the energy that it is stored energy, and we said it's stored in either two spots. It's stored in a object or a field. So in the previous video, we talked about how gravitational potential energy is the energy that is stored within the gravitational field. So in this video, we are going to talk about when it is stored in an object, and that object happens to be springs. Okay, so let's begin. Let's say we have a spring, and this spring is, oh, there we go with purple again. All right, let's say we have a spring, okay, and we stretch the spring all the way out here. So if I were to diagram this drawing, I would say that from there to there, this is our delta x, and when it is at this final position, the spring is going to pull back f of s in this direction. Okay, so the idea here, or the purpose of this diagram, is to show you that when you stretch a spring, over a certain distance, what you end up with is work. Okay, you are doing work to the spring. Okay, now that should be, that shouldn't be any new, right? It's a idea that we've been working off of, but here's a big point here. With this formula, we are now able to come up with the formula for the potential energy of a spring. Okay, so let's follow along. So before we do our derivations, let's come up with the other formulas that are needed. We know that the force of the spring is K delta X. And for all sense of our derivation, we'll just say our x initial will be at 0 meters. Okay, so step one, work is equal to the change of energy. And because we're talking about energy that's being stored in a spring, we're going to call this change of energy the change of spring potential energy, so U sub S. We know that the work formula is force times displacement. If I were to ask you, hey, what's the force that's being exerted? We will say it is the force of the spring. All right, so this is our basic general formula, and then from there we did our substitution based off of the stretching of the spring. I'm going to do one more substitution for f of s here. So we know that f of s is equal to k delta x, and we have here delta x as well. Now we're almost there. This is almost the formula for the spring potential energy formula, but we're going to do a quick little pause, and I want to bring your attention over here off on the side, where I'm going to draw a force of a spring times position graph. So if I were to stretch that spring, the spring would stretch in a linear fashion, okay? And the force of the spring and how hard or how far you stretch it will determine how hard the spring pulls back. And we know this to be true because we know that the formula for a spring, okay, the F and the X are directly proportional, therefore we get a linear line. So this is a good time to do a sidestep review. If I were to ask you, what does the slope of this line represent? Okay, according to our point slope formula method, so I'll do this in a different color. Okay, if this is y is equal to mx plus b, we can see here that the y-axis is the force. Okay, we can see here that the x-axis is the stretch, and therefore our slope, our m, is the spring constant. So the slope is equal to K, the spring constant, right? How stiff that spring is. All right, now here we have a force times displacement graph, and we learned that for force times displacement, if the variables are being multiplied by together, that gives you the area under the curve. So this area under the curve is equal to the work done on the spring. So if I were to ask you, hey, you see this shape here? What shape do we see? Hopefully you all can answer, that's a triangle. And so the formula for the area of a triangle is 1/2 base times height. So 1/2 our base variable is x, and our height variable is the force of the spring. And would you look at that? That almost looks like what we have here, right? The only thing that's missing from this line, where f of s is your height and your delta x is your x, is that 1/2. So if I put that 1/2 there, this now gives us the true formula for the change of potential energy for a spring. So we can say delta US is equal to 1/2 K delta x squared. But if your x initial is equal to 0 meters, this formula simply becomes spring potential energy is equal to 1/2 kx squared. And the idea behind this formula is that when you give the spring energy, the energy is stored within the object itself or within the spring. Whereas before, with the UG formula, the energy is stored within the gravitational field. All right, see you next time. Bye-bye.